cable, cooler charger, faster charge. But most people have no idea why the plug is the real bottleneck. Today we are ripping the curtain back on the tiny piece of hardware everyone touches but almost nobody thinks about, the plug, the cable, and the port. This video explains why a thicker cable can shave minutes off a charge, how a slightly bad connection can throttle power like a dimmer switch, and why worn plugs slowly bleed efficiency without anyone noticing. Stick around because by the end you'll know what you check at the charging station and what actually matters when charging your EV fast and safely. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. Imagine electricity as water in a hose. If the hose is narrow, water flows slow and pressure builds. If the hose is wide, water flows easily and the pump doesn't overheat. The same idea applies to charging cables. The numbers printed on a cable says its gauge. Lower numbers mean thicker wire. Thicker wire means lower resistance, which means less heat and less energy wasted between the charger and the battery. That's why some public fast chargers use massive cables that feel heavy in your hand. But it's not just the cable. Inside the plug, there are metal contacts that must carry thousands of watts. Those contacts have to be made of right metal, have the right surface finish, and be pressed together with the right force. Even a tiny gap or a bit of corrosion can multiply resistance and turn clean amps into heat. When heat appears at the plug, you don't just lose efficiency. You create a hot spot that ages the connector, breaks down insulation, and can trigger safety cutoffs. That's the subtle way a bad plug sabotages perfectly good battery. Connector design is a compromise. Some plugs have many pins for data and safety and a few for power. Others concentrate power into thick contacts. High power charging moves heat from the plug into the cable, the gun, and eventually the charger. That's why some of the high power stations liquid cool the gun and the cable. Yes, the actual cable can be cooled with fluid to keep temperatures down during megawatt level charging or normal charging. It looks wild, but it works because less heat in the connector equals fewer interruptions and faster, steady power flow. Now think about port wear and tear. Every plug-in event rubs metal on metal. Tiny chips, microscopic corrosions, and dirt slowly builds up. Over months and years, those tiny flaws add electrical resistance and you won't see a big red light telling you something is wrong. You'll just notice slower charges, longer sessions, and slightly less range after charging. That slow decline is invisible but real, and it hits fleet operators and regular users alike. There's also the human factor. People yank, twist, or leave plugs dangling in bad weather. Salt, green, and simple mechanical abuse accelerate damage. Manufacturers try to balance durability, cost, and ease of use. So ports are engineered to be forgiving. But engineering can't stop physics. At some point, a worn contact will drop amperage or cause heating. That's why maintenance matters as much as cable size. Let's talk numbers for a minute. Resistance in a cable generates heat proportional to the square of current. Double the current and heat quadruples. That's a brutal law. To push huge current safely, you either need thicker wire or better cooling. That's also why short, thick cables are used in garages and heavy-duty charging, while thin, long cables are common on low-power EVs for convenience but limit how fast you can go. Connector quality affects not only heat but also voltage at the battery. If resistance sneaks in at the plug, the charger compensates and raises the voltage. That can stress the battery management system and change how the pack balances cells. Over time, these small voltage shifts add up to more wear and tear on the electronics, on top of the physical wear in the plug. There's a second hidden effect. High resistance at the plug changes where current prefers to flow. Instead of going into the battery evenly, the system can create local hotspots on the contact surfaces. Those hotspots erode metal, change contact geometry, and create a feedback loop where resistance keeps rising. That feedback loop explains why a connector that seems fine can suddenly go bad after a heavy charge. Data communications inside the connector also matter. Modern plugs carry handshake signals that tell charger and car how much current is safe. If those signals are noisy or if pins are damaged, chargers might be conservative and reduce power. So a battered plug can cause the system to back off even if the cable could handle more. In many cases, the car's safety logic sees an unexpected condition and reduces charging to protect the battery. That's why a seemingly tiny physical issue can change charge times by 20% or more. Lastly, the engineering challenge is not only electrical, it's mechanical, thermal, and chemical. Materials expand and contract with heat. Sealants age under UV and salty air. Insulation gets brittle with time. Engineers chase a moving target, design a plug that works reliably for thousands of cycles in rain, snow, and heat, while staying affordable for millions of vehicles and chargers. Here's the problem nobody pays attention to until it bites you. You plug in at a fast charger, and instead of a steady high power flow, you get a slower trickle or you get a random interruption. People blame the charger or the battery, but often the culprit is an aging plug or a thin cable doing too much work. That silent loss of performance is invisible until repair bills or lost time pile up. Let's break that problem into three parts to understand how to prevent it. First, cable gauge and resistance. Second, connector type and contact quality. Third, wear and tear and the slow decline in efficiency. Cable gauge is straightforward. For a set current level, you want the thickest practical wire to keep resistance down. That reduces energy wasted as heat and lowers the load on the charger's cooling system. But thick wire is heavy and expensive, so engineers pick a practical thickness and then add cooling or shorter runs to meet power goals. Connector types vary. Some countries and chargers use plugs designed for slower charging and portability, while others use dedicated plugs for high power fast charging. Those high power plugs have beefier contacts and better cooling. The compromise is that not every car supports every plug, and adapters introduce more resistance and more chances for trouble. Wear and tear is slow. Regular inspection, cleaning, and replacement schedules make a huge difference here. Fleet operators that track every connector change see measurable improvements in uptime and charging speeds. Home users can do quick checks to look for visible corrosion, feel for loose pins, or notice higher than normal heat at the plug. Replacing a worn cable or getting a charger service is cheap compared to hours spent waiting in line for a slow charge. Now, a subtle engineering insight. The safest chargers are conservative by design. They monitor temperature, resistance, and signal quality and will reduce power if anything looks off. That's good because it prevents fires and damaged batteries. But it also hides the root cause. If you rely on chargers to self diagnose, you might miss the real wear in the plug until the system reduces power repeatedly. Proactive inspection beats reactive troubleshooting here. There are also clever fixes engineers use. Some systems add redundant contacts so that if one path gets dirty, the other still carries current. Others use sprint-loaded contacts to maintain pressure as material wear. Modern plugs use coatings that resist corrosion better than bare metal. For extreme high-power setups, liquid cooling inside the charging gun keeps everything stable during a long, hot session. Here's the sharp, practical point everyone needs. The plug is not a passive part of the charging chain. It's an active limiter and sometimes the weakest link. Thick cables, high quality contacts, good cooling, and regular maintenance let you access fast charging reliably. Ignore them and you'll never see the spec numbers the car maker promised. That one small worn pin can force your car to charge at half speed and you'll blame the battery when the real fix was a new cable. To sum up, thicker cables reduce resistances and heat. Better connectors reduce contact losses and preserve power. Regular inspection prevents the slow efficiency leak that ruins charging performance. The engineering of plugs is subtle but critical. This is the kind of practical hardware detail that quietly decides whether your fast charge is a 5-minute refuel or a 30-minute wait. Here's the key takeaways. Cable gauge matters because resistance grows heat fast and high heat ruins the fast charging speed. Lower resistances means less lost energy and fewer interruptions. Connector quality is crucial because tiny gaps, corrosion, or bad pins multiply resistance and create hotspots. A worn connector causes the charger and the car to back off power to protect the system. Wear and tear is invisible but fixable through inspection and replacement. Fleet operators who act proactively save time and money by avoiding slow charges and downtime. If you want to learn more and go deep dive in the battery management system and learn more about the algorithms and how it's acting or behaving in different modes, you can click on the BMS course in the description. Thank you.